my TTL computer. Today, we're going to take a look at the remote software development stack so that we are developing our my TTL programs on our local laptop. And the basic process is going to be that we create those source files using our favorite editor. We then run those through our assembler, and then we use our 8-bit transfer program to load that up into my TTL computer. So that's the basic flow. And we'll start out today by taking a look at recreating the same looping program that we did in our last video that just did our simple counting. So I have my editor open, and the first thing we do is load A register with a 0. We load B register with 1. We output that to display out and out. The out instruction sends the contents of A. So this will start with 0 on display. Then we do the add of A and B, which will be 1. And then we jump back to the out instruction, which would output the sum, and then we add again. So we've created a little incrementing loop here where we increment and output to the display. Okay, so that's our basic source files created. Now let's run that through the assembler. Okay, and this is the assembler that I have developed. We give the input file name to the assembler and then the output file name. And I just call this a.out. That's just the name that the transfer program is hard-coded to use. It's just a convenient way to do it. Okay, so let's do that. We have our source file done, and we're going to hit our assembler. Okay, so that's it. The assembly is already done. It says we have 9 bytes have been written. It also tells us how many bytes we have remaining, or free program space, basically. So we have 247 bytes before we used up the full 256. Now, the output from the assembler is kind of a listing file for anybody that's done any kind of software programming before. We have the source line number that is it's currently working on. We have the memory location associated with this line. We have the operator load A immediate, showing us what the opcode is in hex 90. And then it's showing us that we have the argument, or the operand, is 0, and it's showing us the hex value. So we see that source line 4, right? Source line 4, load B immediate, load B immediate. We have our opcode value for load B immediate. This time the operand is 1. The value is 1, right? Here we have defined a label, right? And we define a label by using the colon following the text string. So we define the label disp. Here it's showing us the value of that label is memory address location 4, right? And then we're going on to our other statements and finishing out with the jump. Okay, so that was successful, and I don't think we're gonna. All right, so if we tried to upload this right now to my TTL computer, this looks all fine. And if we compared the actual opcodes that we generated versus what we keyed in on my laptop using the switches last time, it would exactly be the same. They would match. But if we loaded this up to the computer with hex loader, it would fail. And I'll give you a moment to think about why that might fail. But the solution to that failure is we need to add one thing. We need to add this org, or origin, statement. And what that does is, okay, without that, we saw that the memory location here in our program started at 0. We can't start our programs at 0 because we already have the hex loader is loaded into my TTL computer first, right? That's using the first 64 bytes of memory is reserved there for the hex loader. So we need to start our program at 64, right? Hex loader really ends at 64 minus 1. So we need to set the origin of our program to be immediately following the hex loader. So let's save that. Let's run this through the assembler again. Right, so we see all the same things. Here we now see our org statement is 64, and we see that our memory address for our program now starts at hex 64. Before it was 0, now it's at 64. And all the other addresses, right, are adjusted and based off of that 64. Okay, so that is our, that would replicate what we did last week. And let's do something a little bit different. So we see here that the load A immediate, the operand was 0 and the value is 0. So that's what we did last video. I'm just trying to show you some of the capabilities of the assembler. Rather than the number 0, let's start ours with ASCII 0. Okay, so this is showing that we have the ability to take different kind of constants. We could have, let's also change this to, no, that was wrong actually. This should have been OX40 is what it should have been. Let's do 64 decimal this time instead of OX40, which is what we should have done. I'm going to save that now. Let's run this through the assembler again. Okay. So now we see that I used decimal 64 as the origin, and here's showing us the value in hex is 40. That's what we should have done before. We should have really done this. Nope, OX40. That's 64 decimal. That's what we really want. So this is correct. 40. And then we also changed load A immediate. Rather than being numeric 0, we used ASCII 0. So we see here, it shows us that the operand to the load A was character 0, and it's showing us the value is hex 30. So I'm just showing that we have the ability to use different types of immediate values in the assembler. So it can actually take decimal values, which we did before as 64. It can take hexadecimal values, which is preceded by OX. It can also be 0B for binary values. All right, so 40 is what we want. Let's do that one more time. Okay. All right, so that's all done. Now we want to transfer this up to my TTL computer, and we use that with the 8-bit transfer program. Okay, I'm going to start that, and we're waiting to start up the hex loader. That's going now, and we had a failure. Let's see what that was about. 41, that all looks good. Let me restart the hex loader. Try that again. Oops. There we go. All right, so that's working now, and just in a loop, we see that here it started at ASCII 0, not at binary 0. All right, let's end that. Okay, so that was a really simple program that showed just some of the basic capabilities of our assembler, really. Let's go over to a different program that's going to be more complicated. All right, so what this program is going to do is it's just going to send out a prompt to this display that says press a key. We'll then, using the terminal, we'll press a key and it will just respond back with you pressed the key, and it'll tell us what we pressed. And that's pretty much all it's going to do in a loop. But the purpose here, again, is trying to show you a little bit more of the capabilities of the assembler. Okay, so looking at our source code, we see the org statement, right? We want to start that at hex 40 or memory location 64. Let's hold off on why I'm doing this jump right now. But the reason why we're doing this jump is I just wanted to move these statements to the front of the top of the program, just so we introduce them before we use them. So this jump is just jumping around these definitions and getting to the start of the program. So what are we doing here with these equate statements? So if you remember, we have hex loader is loaded at the beginning of the memory in my TTL computer, and that's got some things that we can reuse. And really, the thing that we're after here is the get byte routine, right? So we know that what hex loader has the capability of getting a byte, it's checking the COM flag, it's seeing if there's errors, things like that. It's receiving the byte and it's receiving the COM flag. So what we're doing here is we are making those available in our program. We're setting up labels. We're setting a label for get byte, which is the subroutine call that we will make to get the byte from the UART. This is the address of that function. This is the received byte, and this is the address, and this is the COM flag status, and this is the address. So again, we're just reusing code that's already loaded into the computer as part of the hex load process. Now here we are defining some messages that we're going to use, or strings. So here we have a label, right? A label for the string. And here we're using the DSZ directive. So that's basically telling the assembler, define a string. I'm giving you the string here. And the SZ means terminate this string with a 0. So we're not seeing it here, but there's actually an extra byte after the string that's a 0. And I'll tell you why we're doing that in a little bit. Same thing here with the U pressed message, defining a 0 terminated string. Okay, so here's really the beginning of our program. We're loading a immediate with the press a key message, and then we're calling the print routine. After that, we are calling the get byte routine. We're doing some checking on the status here. We are loading the received byte from the get byte, what we've gotten from the UART. We're loading that into the output register, and that's echoing that to the screen. Then we are loading the U pressed message, U pressed the key message. We're calling print to print that message to the screen. We're loading the received byte, and we're outputting that to display. So we're going to get something like press a key. We're going to press the key. We echoed the key back to the display. Then we are saying you pressed message on the screen, and we're going to that will be followed by the key that was entered. Here, we're just outputting a carriage return and a line feed, giving ourselves a new line on the screen, and then we're jumping back to the prompt. So it's just going to be in a loop and do that repetitively. I'm not going to go into this too much, but this is our print routine, and here is basically where it's testing for the 0 at the end of the string. If it's 0 at the end of the string, it returns. So I'm not going to go into what it's doing here, but it basically goes through the string, it gets the character, it outputs the character to the UART or to the display. It increments the location and loads the next byte. And it keeps doing that until it gets to 0. And then that knows that that's the end of the string and it returns. Okay, so that's our program. That should be good to go. We want to change this though to press. Okay, so we wrote a lot more data here, 74 bytes. We could go, nothing too much interesting in the listing portion up here, but this is something we can talk a little bit a second about. Part of the assembly process is handling forward references, right? So and a forward reference is when we use a label before it's defined. And just a simple one is here, right here. We're saying jump to prompt, but we didn't define the prompt label until down here. So the assembler has to account for that. So what it does is when it encounters a label like here, let's jump up to here, up to the top here, see label prompt. No, that's not what we want. Up here, the very top, right? Line 4. We have jump to prompt, but it doesn't know what the value is. And FFFFF means it doesn't know what the value is. So that's from here. So what the program has to do at the end, when it has a reference like that, when it's all done, it has to go back and fix those up. So it would locate any references to prompt and it would patch them, right? Here's the address where the label was referenced, and here's what it's the value it's getting updated to. Maybe more information than you need to know, but that's a key piece of what an assembler does. It keeps track of label references. It allows for forward use of labels before they're actually defined, and then fixing them up later. Okay, so that was 74 bytes. Let's get ready to transfer this up to my TTL computer. All right, I'm not going to start that yet. Need to restart the hex loader. Okay, start that. And hex loader's going. So I made some updates to our 8-bit transfer program. This is fully implementing a mini term. You see that down here, starting mini term. So this is a full duplex mini terminal now. So it has send and receive. We can enter keys here, and it also is implements hardware flow control. So we don't really need to jump out to the other terminal now. We can really just load our programs from hexload here and work right from here. All right, so here we are. We basically up to here in our program, right? We loaded the address for press and we called print. And that's where we are on the terminal right now. So let's press a key, lowercase a. You pressed A, right? So that got the input. Here it output the A that we typed in. We loaded the address for the you pressed message, called print, you pressed. We loaded the byte that we pressed again, and we output that to the screen, A. And then we did carriage return line feed and jumped back to prompt and did it again. So not hugely interesting, but this is actually a big step forward from what we've been doing, right? This is our first case where we got data from the terminal, user data from a terminal. So this is really, right? This is a real program now. We're sending data to the user. We're getting data from the user, and receiving that and operating it on the computer. That's it. So we can break out of the terminal that we were in before. We can resume the terminal. We can add a little terminal argument to our transfer program, and it'll go straight to terminal. Right, and we're back in our code here, and that's it. Okay, so what did we do today? Just to recap, we keyed in some programs from our source editor. We talked a little bit about some of the capabilities of the assembler as far as different different ways we could use immediate values of numbers and decimal and hexadecimal and binary, how we can create strings. And we saw how you can use the assembler. We looked a little bit at that, how the output from the assembler, what that looks like, and the information that gives us. And we also saw how to reuse some of the functionality that's in hex loader, so we don't have to duplicate that in our programs by using the get byte routine and using these equates to access the byte and the received byte and the COM flag status, and some real application interactions with my TTL computer. Okay, not bad. I think next time we will look at some application programs that I have put together so far that are a little bit more interesting than press a key. Okay, that's it. Thanks for watching.